As you probably saw from the abstract that was sent out, I created an abstract that says data is everywhere. It drives marketing initiatives, it shapes innovation. Driverless cars aren't really vehicles, they are data gathering machines. With new technologies like AI, getting data is no longer an issue. Finding value in the data is. In this presentation, I'll offer best practices for getting value from data today, and specific issues that I'll cover are data hoarding, legacy data, cleaning up your data sets, and migrating to cloud. For regulatory and compliance will also come in here as well. And I put in here in a globally connected world. I have to say that's just business speak that I put into the talk. It's true that all of this has a global impact, but let's be fair. Abstracts don't really turn into what the talk actually goes on. A little bit about who I am. I'm the Vice President of Digital Transformation for Pythian. Pythian is a 20-year-old data company. I know that our CEO has spoken at this event in several previous years, so I'm not going to go into a whole lot of detail about who Pythian is and things like that. But I do want to highlight that within Pythian, we have groups of people focused on all these data science, cloud migrations, big data architectures, data governance, data ops, database engines. Anything you like that comes out of here came from one of the teams on here. I talked to them. I learned from them about the kinds of things they're seeing in the industry, but it has been a few years since I was doing any of this like in the field. So you've got to credit them with any good ideas, and anything that I may mispronounce, anything that I may misstate, entirely my fault. So I want to start with this idea about machine learning and the machine learning explosion. A few months ago, the Harvard Business Review put something out called "What's Driving the Machine Learning Explosion?" And the poll quote that I found that I liked: "The mobile internet can now deliver digital technologies virtually anywhere on the planet, connecting billions of potential customers to AI breakthroughs." Right? So as you break this down, and as you read through the article, what it basically says is we have more data than ever. It is easier to access than ever. We have more algorithms than ever, although arguably the best algorithms we're using today, the ones that allow for self-driving cars, we knew about them in the 50s. We just have better hardware now. We can make them operate faster, and the data is easier for us to get to because it's all come to us through the cloud. And for me, running a consulting business, I look at this and I bolded the thing that matters to me. The cloud is what is driving machine learning to come together at this particular point, at this particular time, because it combines all of the others. We are now commoditizing algorithms. We are now saying hardware is somebody else's problem, and we can easily pull all of the data that we could ever want at any time. So if this is what the Harvard Business Review is saying, and it works for me, then my next question, running a consulting business, is which cloud, and how can I harness this, and how can I make sure that I'm in the right place where my customers are needing this, right? So that brings me to RightScale's cloud report from last year, which we can go into all the little details of the numbers here, but that doesn't really matter. What this shows is that the growth of cloud, all clouds, is significant. Either you are already using it or you will be using it within the next year, and the stuff that you're doing now you expect to be doing in the next year. So it's net growth of this. That isn't necessarily coming from you spending less money on hardware. It isn't necessarily coming from you spending less money on traditional stuff. Your new innovation is happening in the cloud, and it's happening with cloud data. Let's find a way to be ready for that tomorrow. So with that context, I wanted to highlight some of the things that we've seen in our experience moving data to cloud, so data pipelines going into cloud, with the purpose of applying machine learning once we get there. Now 90%, now this is where I have to rely on one of our data scientists, a guy named Paul Spiegelhalter, who collaborated with me on this. As soon as I started talking to him about moving to the cloud for machine learning, he said, you know, it doesn't matter if it's cloud or anywhere else. 90% of data science is janitorial work. All of the data that you get before you can really figure out what's valuable in it, you have to spend a lot of time cleaning it up. So in the case where you are already moving to cloud, that's the time to do that janitorial work, because you don't need a PhD data scientist who understands the fitness algorithms and understands all of the proliferation of machine learning in order to be able to clean up the data. That is really a data engineering job, and it's a job for automation. So if we're thinking about moving to cloud and we're thinking about the machine learning that drives that, we need to be thinking about the cleanup of that data on the way in, because that makes it more useful for the algorithms once it gets there. So when you're, so we break this down into two classes of data in any cloud migration. What data do you have that's valuable at rest? That means no one's touching it. It is sitting on a database, in a database, and it just sits there. We don't touch it on a regular basis. That's fine, right? There's a few things that I think are there are a few pieces of data that I find to be valuable at rest. It's the credit card data that you have collected from your customers and you don't want anyone to touch. I would rather have that at rest than in motion, because you have to do all of your compliance around that. Your PCI compliance is based entirely on how you treat data at rest, with a very small amount of how you treat data in motion. The whole idea is to get it persisted to a place where you can govern it well. So the next category is data in motion, and this means anytime you've got data that isn't sitting there, that is somehow being used by you. This is, you've done a SQL query, you have a table that you put into Excel. That's data in motion. How do I maximize the value of that? How do I look at the places where I am moving data and think about what I can be doing to move that data more efficiently? Because ultimately, a cloud migration is all about getting that data into motion and preserving the trail of how it is moving and making sure that it is as valuable as possible at the time when you want to move it. So we'll talk a little bit more about data at rest. I really do think that most of the data at rest is not valuable. I use the example of the PCI environment, which is your environment that stores credit card data. There are analogs for other sensitive pieces of information like your PII and things like that, but anytime you're looking at personal identifiable information, health records, stuff that has a significant risk profile to it, you're going to be wanting to get that into a data store that you don't have to look at very often, maybe once a quarter, and you want it to be very well locked down. Any data at rest, I really look at this way. Like it needs to feel old, it needs to feel stale, and it needs to feel well protected. So for that checklist, when we are conducting a cloud migration of data that is intended to stay at rest, we want to make sure it is auditable. We want to make sure it is encrypted, so that only those with actual access, with verifiable access can open it. Is it recoverable in the case of an emergency? As we all know, we saw some major hurricanes recently. That gave many of Pythian's customers an opportunity to test their data for recoverability. We managed a handful of failovers from Miami to Georgia, from Houston to Colorado. There were, in every single case, things that people had not expected that were challenged by their disaster recovery plan. The disaster recovery plan did not go as planned in every single case. And so now we are working with them to help make sure that that data at rest is well protected and can be resurrected in the case of a disaster. Is it governed? So governance isn't just is it auditable and is it encrypted. Governance means if we have decided as a company that we only want our customer IDs to be stored in one particular format, and then we change that, and then we change our minds. We go from integers to UUIDs, whatever it is, right? We need to be able to apply that governance even to the data at rest. And so if your data is auditable and encrypted and recoverable, but you can't apply governance to it because it is inaccessible, then that's a problem. And finally, is it still there, right? So it is very easy to accidentally, in the cloud, configure a cloud bucket to expire. And if you have done that, that data may not be there when you come back to it 7 or 10 years later. 7 and 10 happen to align with financial storage and legal storage timelines, but they do not align well with the cloud bucket retention factors. Those are more like 1 to 3 years. So not only as you're planning your data at rest movement, should you be looking about where is it and how well governed is it, you need to make sure you know that it will still be there at that point. All of this is really scary because all of these things are talking about are you hitting this checklist for each one of these? And the consequences for not hitting these checklists mean you break compliance, mean that you're no longer able to take credit cards, you're no longer able to handle personal data. That is scary, but the checklist is simple. And if you are able to divide your data into the sensitive data, which stays at rest, and the data in motion that you are able to deal with more easily, and you apply this checklist each time, then moving it from your on-premise like data store to your cloud data store, as long as you can check these boxes, everything's fine. Which then lets us move on, right, to the idea of data in motion, right? And I like this metaphor of data in motion because it fits well with data pipelines, which I'm seeing more and more that we're not doing ETLs, we're not building databases and then doing, doing discrete operations on those databases. We're now looking at every data source, wherever it comes from, and looking at what we need to do over the course of moving it in order to get it into a state that is useful to us, right? I call that a data pipeline. What's interesting about this is you can think about that when you're taking your analytics data and you're ingesting it into your analytics system, right? But you can also take this and say, I've got customer data, it's in a table, and I just updated it to add a new row or add a new feature, like eye color to customer, right? That is transforming the entire data set. You have now said this data set contains a new feature, and that I would call data in motion. So if you start thinking about the data that is moving as the data that is actively being used, and the data at rest as the data that is not actively being used, it gives you a different frame of reference. And then any data that is actively being used becomes part of a pipeline that you're working on. Now, a pipeline is an easy way of moving things from on-prem into cloud. So when I talk about moving the data at rest, that's a big move, a big chunk. You're done, and you leave it there. When I talk about moving data in motion, this is your user data, this is your operational data. You should be thinking about how, instead of thinking about that as a set of tables on a disk, it is a stream of incoming new information that is being changed on the way. So, so that's the context under which I want to cover the rest of this topic, because I think that once you have data in motion, so much is available to you that I want you to understand how we see that from our cloud migration business and how we would like to work on this, or how we think you should think about it. So for data in motion, I want to start with this quote from Quinn Norton that stopped me dead the first time I saw it. It says, over time, all data approaches deleted or public. And when you dig into this, what this really means is that any data that's not useful, that's not in public, will eventually have a lifetime of the disk. It'll have a lifetime of the company that owns it. It'll have a lifetime of the user that stored it, right? And eventually it will be deleted. And that's probably okay, because when you're looking at data in motion, you realize that all of that approaches deleted or public, which doesn't mean you should start deleting it or publicize or making it public every time, but you should realize that it's destined for one of those two categories. And when it is, you will have achieved the full data lifecycle of that data set. I'm sure there are flaws with this, but I find that it's a great way to think about any data transformation, and it's a great way to think about any data set that I'm trying to move into an operational cloud context. So when you're thinking about that, and you're now trying to look at the difference between, so now we've separated into data at rest and data in motion. Now we are also separating into things that are going to be public and things that are going to be deleted. Machine learning is the driver for this migration, right? Machine learning cares about the patterns in the data. It doesn't care about the precision. So if you've got something that is important to you and contains confidential information, and you think it might be trending to public, that's a great opportunity to remove precision, set things up for a pattern, for pattern recognition, and let machine learning do its thing. This generally means removing all of the stuff that makes it hard to move around, the personally identifiable information, well, anyway, let me go on a little bit. Because this is the crux of it. When you start looking at this data, you will either be cleaning it up or throwing it away. And when we think about the idea that machine learning cares about the patterns, not precision, that means we can start sampling. We can start doing aggregations. We can start doing generalizations. We don't need all of the data. A machine learning algorithm that can be trained on a gigabyte of data, when it's given a petabyte of data, it doesn't get better, but it takes a whole lot longer. So the more you can help to set things up so that the machine learning algorithms have enough data to process, but not so much that it's hard to do the experimentation, the better it is. And these are the criteria that you can use, or these are some of the techniques that you can use to make machine learning more effective once you do the migration. Masking PII means that it's easy to share. Data scientists can share them with each other. They don't have to go through all of these crazy, they don't have to jump through hoops to make sure that they're not exposing confidential information. Removing duplicates, like if you've got 500 of the same data point, right? I like this, the example where we have a system that will every now and then, like once a second, raise his hand and say, everything is okay. So if the system is raising its hand every second for 30 days and saying everything is okay, you can probably remove that duplicate. You can probably say, okay, from this time to this time, we are missing no data, and we have a mark every second that says everything is okay. You've lost no information, but you have seriously reduced the amount of extraneous data. You can enrich the data, so this is like, I store eye color over here, and I store, pant size over there. We have decided that for machine learning, it would be useful to have those things together. Bring eye color in to pant size, or bring pant size into eye color as you're moving it through. You still know where the original source of that data is. You haven't changed that. But what you've shown is that a new view of that data is available. You can apply governance. This goes back to the example earlier of changing the way you decided to call a customer. And this happens more often than you might think, right? In the world of acquisitions, one of the things that slows down the integration of IT systems is agreeing what is a customer, what is an employee, what cardinal data do we deal with. And obviously you're going to be indexing and searching. So anytime you have data in motion, you should be looking at how you can put an index together that will make it easier to find all of this stuff in the future. That's the cleaning it up is a pretty standard thing. There are a lot of people who look at that. You can find tons of talks on the internet. It's the throwing it away that I want to get more deeply into because it's the more controversial. It's the harder thing. The fact that people are reluctant to throw away any data in the era of big data means that we end up with stale data sources. And it means we end up with this whole data hoarding mentality. And this leads to the many water-related data swamp, data lake, data, whatever, data stream, data ocean concepts that I see in a lot of the technical papers. Let's figure out how to get from a petabyte down to a gigabyte. And I'll go into a little bit more detail about how we can do that. So data is more useful. And this is a key piece that we look at in our data science practice. Data is more useful when it's less encumbered. And we talked about this before. We talked about the idea that if we've got 500 copies of the same data point over time, we should probably throw away 499 of them and say, and this repeated 500 times. But it's also encumbered when you have personally identifiable information that is linked to it. A great example of encumbrance in data is Fitbit, right? I bought this Fitbit or a version of this Fitbit, in 2007, or so, like right when they first came out. And I loved it. I'm sure that somewhere sitting on some server there is a table that is marked Alex's Fitbit data 2007, right? That is, in the parlance we've been talking about before, that's trending towards deleted because it contains a reference to me. It knows the places that I've been, which are personally identifiable. It knows my gait. It knows my the times of day that I tend to be up and the times of day I tend to be sleeping. Now, all of those pieces of data encumber the idea that there is a pattern in gait that many Fitbits can pull together. So the encumbered data is the data set that says this is Alex, and these are the characteristics that make up Alex. If you remove that, and you throw all this data set all of these data sets into a common data warehouse where you can't extract who had which gait and who had which time frames, now you have a much, much more useful data set that is trending toward public because now it contains nothing that encumbers it. So when you can move a data set from this is trending towards deleted and move it into this is trending towards public only by aggregation or only by sampling, what you've been able to do is throw away a lot of the many data sources and combine into a reliable single data source. And often you can throw away a lot of extraneous information. This is also true for self-driving cars, right? There's been controversy with Tesla about how much data the car sends back to the headquarters. It's a tremendous amount, but it needs to, right? The information about my braking patterns is only useful for the self-driving car industry when combined with the braking patterns of 1,000 other people or 100,000 other cars. The collective wisdom of a fleet of cars, I was hoping that I was going to find that with the advent of Tesla and other self-driving cars, there's a collective noun better than fleet. I like the idea that there might be a collective noun where there are for groups of animals, for cars at some point. So if anyone has an idea, like I think we should try to get this out on Twitter and define that a collective noun for cars is coming, right? But there isn't one yet. So between the example of the Fitbit, where my data from 2007 is not valuable, but the total data set of all people in 2007 and 8 and 9 is valuable, is the same as this Tesla example. The data about the driving patterns of a single driver or a single car isn't useful, but the collective is. And Tesla is using that to create a market advantage as its Fitbit. Tesla has a better stake on it because they can make their cars drive themselves. So when we think about this, with the idea of throwing things away, about the idea that all data tends toward deleted, it leads us to this conclusion. We shouldn't be hoarding valueless data, especially in the cloud. Because if you have a petabyte of data and it's sitting on a net app and you paid for the net app out of capital funds years ago and it is still under warranty and it's still doing fine, there's no added cost for continuing to store that petabyte. But with cloud, because it's so easy to add more data and you never have to think about replacing hardware, data bloat is a real thing. So if you're always looking at your data from the idea that it is either going to be public or going to be deleted, it is either at rest or it is in motion, you start looking at all of your data and realizing that much of it is valueless in the current context, and you can start moving to archival. You can start moving to archival storage, which is much, much cheaper. You can start moving to putting it on tape and sending it in trucks, whatever. Just try not to pay for live data storage of data you're not going to use in the next year. So I want to bring two more examples. I hope I have a chance to get to them, brought from industry. One of them is a strategy for dealing with lots and lots of data. Comes out of our monitoring friends at honeycomb.io. If you imagine all of the many requests that hit Amazon on a daily basis, right? For Amazon Web Services, Amazon the Book, Kindle, whatever, right? one school of thought would say store a record of every single time anyone connected to anything, right? But as you do that, the performance hit that you have to take to store everything is enormous. The monitoring infrastructure required to do that would dwarf the computing infrastructure required to do that. So if that's the case, we need to look to people who've already solved this problem. And the monitoring industry is a good place to start. They know how to use adaptive sampling. They know how to use bucketing. They know how to use like order of mean and and buffering in order to make sure that they're not losing information, even though they're not collecting data. Two great examples of this are bucketing, where you have a bucket of a certain size and you fill it up with each item as it happens. By the end of it, you've got a bucket full that is now full. You store how long it took to fill up that bucket, and you store how many things were in the bucket at the end. And you don't actually have to store each individual item in the bucket. Another one is using a standard deviation from the mean and only storing a data point if it is outside of a standard deviation and doing a rolling standard deviation calculation. Like, these are two really standard, very simple sampling techniques that are used within monitoring. Both of them are applicable to many other kinds of data. So whatever data you collect, if you ask, could we be sampling this and lose no information, chances are good that someone on your team is going to be able to say, you know what, we could do this. Sampling methodology, we could go in, I could talk about for days, but just be aware that throwing away data does not necessarily mean throwing away information, and there are some really advanced strategies for how to do this. And the last thing I want to talk about is what about regenerating data? The pipeline is more important than the data when you talk about astronomical observation. And I'm going to dip into some science here. I hope you guys are ready to come with me. If you look at that picture of a telescope, and that's built on the top of a mountain, say 13,000 feet high, and chances are pretty good that they didn't run fiber up there. So those mirrors you're looking at, those are 8.5 meters across, each of them. When that thing stores data, it takes a picture of the sky that is about 500 megabytes. Just storing that 500 megabyte data, that 500 megabyte picture, already is a problem when you're trying to then send that data off of the mountain and into a lab at the bottom, right? Let me go into it a little more detail, right? So this observation, I happen to know something about. This is 512 megabytes of image data, and the astronomical data that was generated out of it was 5 gigabytes. That was just for one astronomer doing one set of analysis. Now, when the astronomer left the mountain, carrying with him or her a USB stick that contained the image data, and they also were carrying with them a pipeline definition. Here is how I generate the 5 gigabytes. Here's what I did while I was on the mountain to generate the astronomical data that I then based my research on. We can learn from this, right? Because when an astronomer wants to replicate the results when a second astronomer wants to replicate the results of the first astronomer, what they need is that 512 megabytes of data and the description of the pipeline. And they will end up recreating the 5 gigabytes of data that is required, and they will come to the same conclusion. Science works this way. It's great. We can learn from this. If the thing we do is pull in analytics data, use that through several series of pivot tables to create a new a new customer segmentation. The more interesting thing is the resulting customer segmentation and the process to do that than all of the intervening data sets that get you. So when you're planning when you're planning something with your data, think about what pieces of data do you really need that have information, and how can you regenerate the data product in the future using the same methodology, or maybe even using similar methodology, so that it's the methodology that you're testing, not your ability to store multiple gigabytes of data to look at them again in the future. So I like to use this as an example because it shows you that when you are constrained in the amount of bandwidth you have, you've come up with new ways of shipping information that doesn't involve shipping data, and that we can learn from our friends who in academia about replicating results, and we can use that in our discussion about what do we store in cloud and why. So what? I'm going to leave you with a few things to consider. If you think about all data trending toward deleted or public when you are dealing with data in motion, knowing that the unencumbered data is more shareable, more useful, the reproducible results that are generated out of your data sets are more important than hoarding all of the data that you could ever grab. And whenever you are putting data in motion, it should become more useful as part of that motion. So we use these at Pythian as we are looking at cloud migrations of data pipelines, so that as we are doing this, everything gets more valuable and more useful and more well-governed and more like it all gets better. But it is something that you guys can apply within your own organizations anytime you engage on in a data migration. Thank you very much.